Third one, frequency control of induction motor. The torque and speed of an induction motor can be controlled by changing the supply frequency. From the equation number 31, that phi equals to VA by Km omega is equals to BVS by Km omega. We can notice that at rated voltage and rated frequency, the flux will be rated value. If the voltage is maintained fixed at its rated value, while the frequency is reduced below its rated value, the flux will increase. This would cause saturation of air gap flux, and the motor parameters would not be valid in determining the torque speed characteristics. At a low frequency, the reactance will decrease and the motor current may be too high. This type of frequency control is not normally used. If the frequency is increased above its rated value, the flux and the torque would decrease. If the synchronous speed corresponding to rated frequency is called the base speed, that is omega b. The synchronous speed at any other frequency will become now omega s equals to beta omega b, and the slip s equals to beta omega b minus omega m divided by beta omega b, which equals to 1 minus omega m by beta omega b. That is equation number 56. And the torque expression, as in the equation number 18, will become that Td equals to 3Rr Va square divided by S. Omega S now will become that beta omega b of Rs plus Rr by S whole square plus Xs plus Xr whole square. This is equation number 57. The typical torque speed characteristics are as shown here for various value of beta. The three-phase inverter can vary the frequency at a fixed voltage. If Rs is negligible, then the maximum torque at a base speed is given by the TMB at base speed is given by 3 Va square divided by 2 omega b of Xs plus Xr. Let it be 58 now. Now the maximum torque at any other frequency is given by Tm is equals to 3 by 2 omega b of Xs plus Xr of Va by beta whole square. Let it be 59. Now the corresponding slip Sm is given by Rr divided by beta of Xs plus Xr. Let it be equation number 16. Normalizing equation number 59 with respect to 58, then you are going to get Tm divided by Tmb equals to 1 by beta square. Let it be 61. From this, you can write Tm beta square equals to Tmb. Let it be 62. Now, from the equations number 61 and 62, it could be concluded that the maximum torque is inversely proportional to the frequency square, and Tm beta square remains constant, similar to the behavior of DC series motor. In this type of control, the motor is said to be operated in field weakening mode. For beta greater than 1, motor is operated at constant terminal voltage and the flux is reduced, thereby limiting the torque capability of the motor. For beta between 1 and 1.5, the relation between Tm and beta can be considered approximately linear. For beta less than 1, the motor is normally operated at the constant flux by reducing the terminal voltage Va along with the frequency so that the flux remains constant. This is regarding frequency control of an induction motor. The fourth one, voltage and frequency control of an induction motor. If the ratio of voltage to the frequency is kept constant, then the flux remains constant as flux is equals to Va divided by Km omega. Equation number 59 indicates that the maximum torque, which is independent of frequency, can be maintained approximately constant. However, at a low frequency, the air gap flux is reduced due to the drop in the stator impedance, and the voltage has to be increased to maintain the torque level. This type of control, usually known as Volt's hedge control. If omega s equals to beta omega b and the volts to frequency ratio is constant, so that VA divided by omega S equals to D. Let it be 63. The ratio D, which is determined from the rated terminal voltage Vs and the base speed omega B, is given by that D equals to Vs divided by omega B. Let it be 64. Now substituting VA from the equations 56 and 57 is the torque TD, and the slip for the maximum torque is given by Sm equals to Rr divided by Rs square plus beta square of Xs plus Xr square, entire denominator under the square root. Let it be equation number 65. The typical torque speed characteristics are as shown in this figure. As the frequency is reduced, beta decreases and the slip for maximum torque increases. For a given torque demand, the speed can be controlled according to the equation number 64 by changing the frequency. Thereby, by varying both the voltage and the frequency, the torque and the speed can be controlled. The torque is normally maintained constant while the speed is varied. The voltage at a variable frequency can be obtained from three-phase inverters or cycloconverters. The cycloconverters are used in very large power applications like locomotive cement mills, where the frequency requirement is 1/2 or 1/3 of the line frequency. Three possible circuit arrangements for obtaining variable voltage and frequency are as shown here. In the first figure, that fixed DC and PWM inverter drive, the DC voltage remains constant and the PWM technique are applied to vary both the voltage and the frequency within the inverter. Due to the diode rectifier, regeneration is not possible and the inverter would generate harmonics into the AC supply. Whereas in the second circuit, that is variable DC inverter drive, the chopper varies the DC voltage to the inverter and the inverter controls the frequency. Due to the chopper, the harmonic injection into the AC supply is reduced. And in third circuit, that is variable DC from dual converter and inverter drive, the DC voltage is varied by dual converter and the frequency is controlled within the inverter. This arrangement permits regeneration. However, the input power factor of the converter is low, especially at high delay angles. These three circuits are the voltage source induction motor drives. This is regarding the voltage and the frequency control of an induction motor. If this video is useful, please like, share and subscribe.